We're still working with properties of integrals, but this time we're looking at trig functions. Now, these you could actually do in a calculator, and I'll just bang one out real quick for you. So just make sure you're in the right mode. So math 9, pi to 2 pi. This one's sine of x. You can already see it's kind of a lot to type in. So if there's a quicker way to do it, that's sort of where you want to be. Alright, so you got a -2 as a result. So let's see how this actually plays out. Alright, now they gave us a relation here, and that is that from 0 to pi, the sine function has an area of 2. Alright, let's just draw a typical sine function. I'll just do it off on the side here. So from 0 to 2 pi, we have equal parts area above and below the x-axis, so we know the total area, the net area from 0 to 2 pi is going to be equal to 0. But what they're telling us is that if we only go to pi, then we're looking at just that top arch, this piece here, would have an area equal to 2, all right, which implies that the corresponding area below the axis would be equal to -2. All right, so that's actually our answer to the first part, part A, -2. It says from 0 to 2 pi, well, that's the whole distance. The area, if you take the 2 and add to it -2, you're going to get a 0, so there you go. But then the question becomes, well, what happens if you only go half the distance from 0 to pi? So let me get this 2 out of here, bring it in, split this puppy right down the middle. It looks like we have 2 equivalent areas. All right, so it's reasonable to assume that each one of these is going to have an area of 1. All right, so from 0 to pi over 2, we'll have an area of 1. So now we start kind of expanding on that. From 0 to pi, 2 plus the sine of x. So let's split that up, 0 to pi of 2 dx plus 0 to pi of sine x dx. All right, for a constant, we learned on the previous page that, and also through the properties, that all you have to really do is find the length of the interval and multiply it by the height, because it's horizontal. It's a horizontal line, and you'll have the area of the rectangle. So the difference between the bounds gives you the length of the interval, which is pi. The height is 2, so 2 pi would be our area. From 0 to pi, we already know that was given as 2. So 2 pi plus 2, and you have it. All right, so let me just kind of bring that a little closer. And that would be your final answer for that part. From 0 to 2, with a constant multiple, I could rewrite that, from 0 to pi with a constant multiple of 2. I can rewrite it as 2 times the integral over the interval of 0 to pi of sine x dx. And again, we know this piece is equal to 2 that was given. 2 times 2 is going to give us 4. All right, part F, that's kind of a fun problem. I'm actually going to take the original diagram here and bring it down. I'll just kind of tuck it in over here. I'm going to get rid of some of this extra fluff. All right, now this is saying that we're going from 2 to pi plus 2. But then we're dealing with the sine function where instead of having an x, it's x minus pi over x minus 2. All right, so this is telling us that we're actually shifting the graph to the right 2 units. All right, So as a ballpark, 2 units is going to be somewhere in the neighborhood, well, pi over 2 is about 1.57, 3.14 is pi-ish. So somewhere around here, we'll call that 2. So whatever this distance is, every point is getting shifted that number of units to the right. So I'll just take all the important points and do it that way. So we're looking at a graph, something like this. But it's the same graph. It's just now going out to 2 pi plus 2. So it's starting at 2 and it's going out to 2 pi plus 2. All right. So instead of having special points at 0, pi over 2, pi, 3 pi over 2, and 2 pi, it's really going to be all of those special points plus 2. So this point right here is going to be pi plus 2. So what this is telling me is to find this area. Same graph though, just shifted. So whatever the area was before is what it's going to be now, and that area is equal to 2. Now because sine functions, so in G, because sine functions are odd functions, if the bounds are opposites of one another, then you're talking about areas that are going to cancel each other out. So we're going to have equal parts negative and positive areas on the opposite sides of the y-axis, so this is going to go to 0, regardless of what u is equal to. All right. H and I, we start getting, making kind of a bit of a departure from where we started, but we can still take our original graph and modify it. Again, I'm going to get rid of the bits and pieces. So this is saying, again, go from 0 to 2 pi, but our frequency is 1/2. All right, so that's what that's telling me is that I'm only going out, or I'm only going to get, I almost said that backwards, I'm only going to get half of a sine wave in a 2 pi period. All right, so this is what half of a sine wave looks like. What this is telling me to do is stretch that over a 2 pi period. So this point goes here. This point would go here. This point would stay put. Oh, that's terrible. Let's try that again, shall we? Using a technique I like to call the right way. So that's essentially what the graph ought to look like. So this is the sine of x over 2. All right. So you think about what happened. Well, the height remained the same, but the width doubled. Well, when you're finding areas, if you double one dimension, you double the area. Double them both, then you quadruple the area. All right, so the original area was 2 for one arch. Well, now we're going to double that. So the area is going to be 4. And that's going to allow you to avoid having to get into all the different, half angle identities and stuff like that for trig functions. All right. For I, we're onto a cosine function. Let me just draw a quick sketch of that. Now, as we know, a cosine function is just a shifted sine function. So it's saying to go from 0 to pi, here's pi, if you look at this, you see that we're looking at equal parts above and below the axis. So regardless of what these areas are, they're going to be opposites of one another, and so therefore they will cancel each other out and give you a result of 0. Alright, so that's pretty nice. Well, I didn't box any of the others, so I'm not going to box this one. Alright. So then you get on to numbers 4 and 5. Use areas to evaluate the integral. So it's not a matter of just popping it into your calculator. We need to use areas to come up with these values. So what we'll do is look at this function. Y equals the square root of 4 minus x squared. If I square both sides and add the x squared to both sides, I get a circle with center at 0, 0. And radius equal to 2. Alright, so that's good news. We know how to find the area of circles. Alright, but because this is indicated as a positive square root, I only want the top half. So if I draw this circle, well, that was pretty awful. I mean, that's not much better, but we'll take it. What this is saying is that I only care about this piece. Alright, well, we know the radius is equal to 2, so area is equal to pi r squared for a circle, poor quality circle. Area of a semicircle is going to be 1/2 pi r squared. So 1/2 pi times 2 squared is going to be equal to 2 pi. Now the last one, use areas and your knowledge of discontinuous functions to find this. Right. Now there is some funny business going on with this one that we'll talk about a little bit later in the course. But for now, we're just kind of looking at this and saying, okay, what does the absolute value of x really translate to? Again, we're just going to kind of look at it as a function. Y equals the absolute value of x over x, which is y equals plus or minus x over x. Now we have domain considerations here, but we'll get to that in a sec. All right, this translates into two separate pieces. Y equals negative x over x. Y equals positive x over x. So that furthers to say y equals -1, horizontal line. Y equals +1, same deal, horizontal line. All right. So I'll just draw a quick sketch. This whole thing starts at an x value of -1 and ends at an x value of a +2. All right. So it's a question of, all right, well, which piece is appropriate under, which circumstance? Well, that goes back to the original function. If I take a -1 and pop it in for x here, so if I say, just going back to this guy here, what is y of -1? I'm looking at the absolute value of -1 over -1. 1 over -1 is going to be -1. All right, so it appears, and before I finish that thought, I'll put in the 2. It appears that for negative values of x, it corresponds to a -1 for y, and for positive values of x, it corresponds to a +1 for y. The one issue is 0. If I plug in a 0, I'm going to get something that's undefined, actually indeterminate. All right. So we have an issue there. So we're looking at a -1 here, so I'll pop a -1 there, a +1 here. We're looking at a horizontal line up to, but not including the 0. Alright, that dash is kind of making life miserable for me here, so let me do it like this. I'll do an open circle, and actually I'll make it red. And then an open circle here, going out to a +2. And it's these two areas that we're looking for. This one here, and this one here. Alright, so when we have that in mind, well, first thing we can realize is that whatever this area is here is going to cancel out with this area there and make the two irrelevant. So really the only thing I would care about is whatever this area is, going from 1 to 2. Alright, so it actually makes the part where x is equal to 0 irrelevant, because it's going to be equal to 0 for both pieces, but they cancel out anyway. So this area has a length of 1, a height of 1, so its area is equal to 1, and so therefore the final answer is 1.